Hello everyone, welcome to Stat 310 Lecture 19. We're going to move on to a new chapter, Chapter 12, which in particular focuses on another important scenario that arises in practice. And we use a very common and very useful technique called analysis of variance, or ANOVA. It's in Chapter 12. So just to kind of give a brief summary of where we're at in the course. So we spent, I would say, a lot of the time on chapters 8 and 9, which focused on first laying the foundation first for how to do parameter estimation in chapter 8, and then how to do hypothesis testing in chapter 9. And then having spent a fair bit of time on that, the course has now shifted to where we're, like chapters 8 and 9 largely focused on the setting where you have IAD sample, independent samples from a single sample. But as I mentioned, in practice, you get, much more, we don't always get kind of that scenario. And so in chapter 11, which we covered, in chapters 7, in lectures 17 and 18, we focused on two samples. So going from one sample to two samples and, finding statistics for each of those samples and then kind of trying to test whether those two samples are significantly different or not. And so chapter 12, analysis of variance, is kind of a step on top of that, where we now don't just have two samples, but we have potentially more samples, and we're trying to see if there's differences between them and also do kind of estimation across those different samples. So in particular, today's lecture is going to focus on, I guess, the simplest form of ANOVA, which is one-way ANOVA. And in particular, we're going to look at both the estimation and the testing problem associated with ANOVA. So as I mentioned, chapter 11 focuses on two samples. And we saw how we could kind of test whether there was a significant difference between those two samples. And so a natural sort of extension to that, which arises a lot in practice, is what if there's more than two? So you have say I samples here. So I here is a number that we're going to use to kind of be consistent with the textbook. I is the number of samples or the number of groups. So I is bigger than 2. So for example, you might have we're in the we're kind of in the middle of talking about voting, or potentially the voting's kind of already been counted. So we have samples from 52 states. So here I equals 52. And you potentially expect there to be differences across the states, or you would expect there to be differences across the states. And so here you've got kind of 52 different groups or samples. And an example that I'll refer to today is we have samples from different labs. So for example, there might be various different labs across the country that are interested in studying a particular chemical or disease. And so each of these labs is, even though they're testing the same thing, they might in principle come up with different results. And so you might potentially have samples from different labs, and these correspond to different groups, and the number of different groups is typically going to be bigger than 2 in that case as well. So just to kind of go back to our statistical framework and how things are in kind of this setting of this ANOVA setting where you have multiple groups compared to earlier. So here, your data here, and I'm going to try to be consistent with the textbook here. So your data here is your YIJ, where now you have two subscripts because you have one subscript for which group you're in, and then another subscript for within that group what sample are you referring to. So here I is the number of groups, so either the number of states, and J here is the number of samples per group. So we're gonna, for simplicity, assume that the number of samples in each group is the same. So then in the context of the statistical model, what we're going to assume is that for this one-way setting, you have your overall your YIJ has an overall effect, so that's the overall mean. And then you also have a group effect potentially. So this is kind of the effect on each state. So you might imagine that, some percentage of people across the whole country are going to vote Democrat or Republican, and that kind of corresponds to the overall mean. But within each state, so say Wisconsin or California or South Carolina, there's going to be a group effect, like a state effect. That percentage is going to change, and so that's going to be modeled by this alpha I, and then you have some independent noise associated with that. And throughout this chapter, and as I mentioned in chapter 11, chapter 12, and then later we're going to look at chapter 14, we're going to assume that everything's normal, because that allows us to kind of compute statistics in a more efficient way. And a lot of what I say can be applied to more general settings, but we're going to kind of stick with the example of the assumption of normality. So here, this is our model that we're dealing with, where we have the overall mean mu, and then the group effect alpha I. And we also need this additional assumption that the sum of the alpha i's is 0. This assumption kind of makes intuitive sense in that the overall group effect on average should be 0. So if you consider the state example, because we have an overall mean, what the alpha i's is measuring is the deviation away from that mean. And so if you kind of average across all states, that should be 0. So the parameters of our model here, we have the overall mean, then we have the alpha i's, the state effects, and then we also have our sigma squared, which is the variance of our noise. And so the focus of today is going to be on components 3 and 4 of our statistical framework, which are the estimators or statistics. And we're going to get different estimators and statistics depending on whether we're considering estimation or testing, and we're going to see kind of those come out. And then we're going to look at the distribution of statistics, which in the case, because we have things that are nice and normally distributed, statistics like the normal distribution, the chi-squared, and the F are going to come out because things are nice and normal. And so in particular, a good example to keep in mind, and one to, I guess, check your calculations on where you have all the data, is in page 478 of the textbook. There's data from collected from 7 labs where there's 10 samples from each lab. And so here your I equals 7 and your J equals 10. And I'm going to kind of refer back to that example. So, when you look at that, when you're going through the concepts from this lecture, it'll be useful to kind of go back to that example. So just let's first focus on estimation. Okay, so we have that. So we have our model, which is that Yij is equal to mu plus alpha I plus epsilon ij, where we know that epsilon ij is normal, mean 0, and variance sigma squared, and they're all independent. So we're assuming throughout that these are independent. The noise is independent across both the sample within each group, and then also across the groups. And then we also have this assumption that the sum of the alphas is 0. And again, the reason for that is because, the overall deviation away from the mean, if you add it all up, should be 0 because you have this overall mean. So always keep in mind that the interpretation, so I'll put interpretation, mu is like an overall mean. And then alpha I is the group effect. And so if you want to, another way to think about it, if you want to kind of, think about it differently is that, so if we let mu I equals mu plus alpha I, mu I is the mean of group I. Okay, so that's why it makes sense that the summation of the alpha i's is 0, because mu I is kind of the overall mean is the mean of each group. So alpha I is really it's not an overall mean per se, it's kind of the deviation away from the mean across all of the J samples or groups. So so we have our parameters here that we're trying to estimate. Parameters here are mu and then alpha I equals 1 to I, and then our sigma squared. And for now, we're going to focus on the estimation of the mu and the alpha i's, because that's actually, you can separate that out from the estimation of sigma squared. Later, I'll talk about how we estimate sigma squared as well. There's actually a few choices we have, and I'll sort of talk about what kind of makes the most sense in that context. So we're gonna find maximum likelihood, and this turns out to be the same also as the method of moments estimate. Maximum likelihood estimator for mu and then the alpha i's. Okay. So what we can see is that we have that f of we'll say yij as a function of mu, alpha I, and sigma squared. So those are the parameters, are 1 over square root of 2 pi sigma x of yij minus mu minus alpha I squared. And so if we look at, I'm going to leave this for you as an exercise, the negative log likelihood. The negative log likelihood, so when we kind of take the likelihoods by multiplying everything out, is just, and then take logs, that's going to be we're going to get 1 over 2 sigma squared okay, and then plus ij times and we're going to get log of sigma times square root of 2 pi. Okay. So to find, and then we also, the other thing to remember is we also have this constraint that the summation I equals 1 to I of alpha I should equal to 0. Okay, so so we can differentiate and set to 0. And so if you differentiate with respect to, so for what we can then say is for first mu hat, we're going to get just one equation out of that, which is that and this is something that that you can check. You're going to get that minus mu hat minus alpha hat I. That whole thing should equal to 0. And then for the alpha hat i's, if you differentiate, now you're just going to get you're going to actually get I equations out of this, which is going to give you that should equal to 0 for I equals 1 to up to I. And then we have this additional constraint, and then you have the constraint that the summation I equals 1 to I of alpha hat I should equal to 0. Okay, and so when you kind of go through the math in this case, you can see that therefore we have that mu hat is just equal to 1 over ij and then this is going to be yij, and I'm going to use this notation y bar dot dot. The dot kind of means that we're taking the average over both the subscripts, And then the alpha hat I is going to be equal to 1 over j yij, and then minus y bar dot dot, which is just going to be y bar I dot minus y bar dot dot. So y bar I dot kind of just means the sample mean for, so I'll just write it out. So y bar I dot is just equal to the sample mean of, okay, and so this in some sense makes, like, this kind of makes intuitive sense. So therefore, and you can check that the summation I equals 1 to I of alpha hat I is equal to 0. That's something that's straightforward to check because we have, the overall mean should be equal to the mean of the mean of the means of the groups. So you can the calculation is probably secondary here. It's just differentiation. What's more important is that the interpretation here, I think, makes a fair bit of sense. So mu hat is y bar dot dot, and so this is kind of the overall sample mean. And then we have that alpha hat I is equal to yi minus y bar dot dot. This is the sample group effect. And so you can kind of see here, if mu hat I equals to mu hat plus alpha I hat, that just equals to yi bar, which is the group sample mean. Okay, so these give you pretty good and pretty intuitive estimates for the overall, for both the group effect and for the for the group effect and for the overall effect. Okay, so that's kind of estimation, which is straightforward enough. And so just as an exercise, for the labs example on page 478, find y bar dot dot y bar I dot mu hat and alpha hat I for I equals 1, 2 up to 7. Okay, so essentially find all of these key statistics in that. So, where the overall mean is an average of these 70 numbers, and then for each lab, you're just going to get an average of 7 numbers. And you can also check that that summation I equals 1 to I of y bar I dot equals summation I equals 1 to I, which is going to equal to I times y bar dot dot. That's something you can check. Okay, so that kind of covers the estimation of the mu hat and the alpha i's pretty easily, and it's kind of something that you can hopefully get comfortable with pretty soon. So where the question gets kind of interesting is if we look at let's look at the hypothesis testing here. So for I equals 2, which is what we covered in chapter 11, we wanted to test whether group means were the same. Group means were the same or different. And here we're doing something similar. So for general ANOVA, so this is for general I, we have that H naught here is that alpha 1 equals alpha 2 equals alpha I, and that should all be 0. So there's no group effect. Okay, so this, like, for the labs, that would be saying that there's no significant difference across the 7 labs, and that's kind of what you, in some sense, ideally want. And then the alternative, H1, is just going to be like the complement, I should say, of H0. That's probably the easiest way to express it, that it's possible that any pair of the I's is different. So this is a little bit different in the sense that we're actually like placing a lot of constraints on H0 to say that all of the groups have exactly the same mean. So another way to think about it is that under H naught, we have this model that Yij equals mu plus epsilon ij. And if we look at H0 union H1, which is the complement plus, we have this model. So let's say. So the statistical model under H naught is Yij equals mu plus epsilon ij. So this is like saying there's no group effect. And under H0 union H1, so this is a group effect. Okay, so so the question is, so how can we develop a good test for this? So, intuitively, you can just look at the alpha hat I's and see if they're close to 0. But there's actually like I of them, so it's a little bit hard to kind of think about like what that test might look like. So we're gonna kind of develop a general testing framework, which very much exploits the normal distribution and properties of the chi-squared and the f and so on. So this I'm going to kind of talk about as the probably the most kind of the newest and most interesting thing that you'll learn from this lecture, or useful, is the sum of squares decomposition. Okay, so the sum of squares decomposition is as follows. So we have the following decomposition. I guess I'll just say we have following. Okay, so let me just kind of talk about all of these three terms. This is the overall sum of squares. So it looks like it's very related to the kind of the variance of a sample. If we treated kind of all ij's as just one big sample, it's kind of related very closely to how we would estimate the variance for that. This is the variance. I'll say, no, I won't say sum. This is the sum of squares within groups. This is the sum of squares within groups. And this is the sum of squares between groups. Okay, so I'm just going to, like, another way to kind of write it out in short form is we have the SS total is equal to the sum of squares within plus sum of squares between, where we have that SS total is the So note here that these are all just statistics. Okay, so just to interpret the sum of squares within, you can see that what we've done is for each of the I groups, we're just looking at the difference between each of the sample within each group and the overall and the mean of each group. So to interpret SS total, it's just like it's as though we just ignore groups completely and we just treat the IJ samples as a whole, and we look at kind of the difference between each of the samples and the overall mean. And then the SSW is just looking at, if you treat each group separately and just look at the difference between each sample within a group and the overall sample of that group and the overall mean of that group, and then you add up across all of the I groups, and the sum of squares between that just looks at kind of, if you imagine that you've got, now you have your I group means, how different are those group means from the overall mean? Okay, and so let me just show you why that's true. So just, it's pretty like easy algebra, but I'll just do it anyway. So why is the composition true? We can see that SS tot is equal to okay, and that equals to so then we're going to subtract off the group mean and then add the group mean back on, and okay, and we can simply just expand out the square to get okay, and then we're going to get our cross terms. Okay, and it's fairly straightforward to show that this is just equal to 0. And the way you can show that is if you do this sum, if you do this sum, it's going to cancel out. If you just kind of sum over the j's, you can see that summation j equals 1 to j of yij minus yi. That's just going to equal to 0. So therefore, that's why you get that is equal to 0. And so this is equal to and then when you can see that the j is just going to get summed out because there's no j's in the expression for the second term, and so this is going to be the sum of squares within and then the sum of squares between. And so the intuitive idea here is that under h naught, sum of squares within should be much bigger than sum of squares between. And we can also think of this from an estimation point of view. So SS tot here is equal to is just yij minus mu hat squared. SS the SS within is just equal to one j of yij minus mu hat minus alpha hat I squared. And the SS between is just equal to j times summation I equals 1 to I of it's alpha hat I squared. Okay, and so that's kind of another way to interpret this. And clearly, if SSB is if the alpha I should in principle be 0, then that SS between should be equal to that SS between should be very, very small because the alpha hat i's should hopefully be very, very small. Okay, so now let's look at so let's look at the distribution of SS tot, SSW, and SSB under H naught. So this is under the null hypothesis. We have that under H naught, we have that yij is equal to mu plus epsilon ij. Epsilon ij is normal, mean 0, and variance sigma squared. And so so you can calculate that. So here we have that the alpha I is equal to 0. So for all I. Okay. So you can see that so the sum of squares total is going to have a chi-squared distribution with ij minus 1 degrees of freedom. So this is the way to think about that is that sum of squares total is just equal to, or I equals 1 to I summation j equals 1 to j yij minus y bar dot squared. So you have ij total samples, and you lose 1 for the overall mean y bar dot. Okay, so then the next thing is to note is that if we look at so if we look at now the sum of squares within, we have that Yij is distributed normal with mean mu and variance sigma squared. And we have Yi bar dot is going to be mean, it's going to be normal with mean mu and variance sigma squared over J. And so what you can see is that if we let equal to J equals 1 to J of Yij minus Y bar I dot squared, the mu's are going to cancel out. I'm sorry, there should be a sigma squared in there, shouldn't there? Yeah, so this should be SS total over sigma squared, I'm sorry. And similarly, if we have SSW over sigma squared, that should equal to, sorry. SSW divided by sigma squared. That should have a chi squared I times, and then we have J minus 1. And so the intuition behind that is that for each sample, for each group, I should say, we have a chi squared J minus 1 chi squared J minus 1 distribution, and we add up I of them. Okay. And then finally, if we look at SS between, that's just equal to J times Y bar I dot minus Y bar dot dot squared. And you can also show that SSB over sigma squared is going to have a chi squared with I minus 1. And this again has very similar logic that so this has very similar logic, since we have like sorry, I just lost my train of thought briefly. But so what we have in this context is we have Y bar I dot is normal with mean 0 and variance 1 over J, and then Y bar dot dot is normal with mean 0 and variance 1 over IJ. And you're kind of adding, so you're adding up, so there's I means, and you lose 1 degree of freedom. You lose 1 degree of freedom because you estimate overall mean. Okay, and so I just want to, so what we essentially have is that we have SS total equals SSW plus SS between. And then under H naught, the distributions are like, are chi squared ij minus 1 is equal to chi squared I times j minus 1 plus chi squared I minus 1. Okay, and I just kind of wanted to talk a little bit about these, the degrees of freedom and how to interpret these things, because I think the intuition behind it is actually very, very nice and very, very clear. So the intuition behind this, I think, is very, very nice and very, very clear. So the idea here is that we have so we have ij samples in total. We can think of SS total as the overall variability across all ij samples, and that's why we have ij minus 1. That's why we have ij minus 1 degrees of freedom. We have ij minus 1 degrees of freedom for that reason, because we lose 1 for the sample. And then we have, for each I, we have j samples. And so SS within looks at variability within each sample. So SSW looks at variance within each sample, and so therefore we have I times j minus 1 degrees of freedom. So and then we have I group means, and so SS between looks at how different these group means are. So this is just looks at variability across groups. And so one thing you can see is that you can see that the sum of squares, the degrees of freedom, kind of add up. We have I times ij minus 1 is equal to I times j minus 1 plus I minus 1, and that's something that you can kind of So this is this is the degrees of freedom total. This is the degrees of freedom within. And then this is the degrees of freedom between. Okay, and so that's kind of a nice interpretation of what's going on. Okay, and so now let's look at the example of how we can actually. So how can we use this to find an overall test? An overall test. So intuitively, if SSB is large relative to SSW, we would reject H naught, and vice versa. So how do we compare them? So if you look at So the statistic, or the test, or I'll just say the test statistic here, the test statistic here is the F statistic because it's kind of a ratio of independent chi-squares. If we look at F, which is the between, and then divide by the degrees of freedom, and then we look at the within group and then divide by the degrees of freedom there, which is I times j minus 1, then we should have under H naught, F should have a distribution that is like from the F distribution, I minus 1, and then I times j minus 1. And so this should be true sort of under the null hypothesis that alpha 1 equals alpha 2 equals alpha I is equal to 0. Okay, and so this kind of gives you a way to, reject or accept the null hypothesis. So if F is above a threshold, thresholds, and again, this, depending on alpha, remember that alpha is kind of the size of the test. So maybe I'll just say that if F is, that threshold depends on alpha and that distribution, then we would reject H naught. Otherwise, we'd accept H naught. Okay, so let's return to the example with 7 labs and 10 samples per lab. And we're going to kind of construct this, what's called the ANOVA table, because we're kind of calculating a lot of things and it's important to keep track of all of them. And so what we kind of want to have in this table is this, like, to keep track of everything, we're going to have the, this is going to be the SS between, the SS within, the SS total. And we can also look at the degrees of freedom, the sum of squares, and then we're going to look at the mean squared, and then we're going to get the F statistic out of it. And so I'm going to first talk about it in general. So in general, the degrees of freedom we're going to have here are I minus 1, I times j minus 1, and then I j minus 1. And then we're going to have the, this is going to be the sum of squares between the sum of squares. So maybe I'll write it this way. So this is the between, this is the within, and this is the total sum of squares. And so this is going to be the sum of squares within, this is the sum of squares total. The mean squared here is going to be SSB over I minus 1 when we divide by the degrees of freedom. And then this is going to be I times j minus 1. And then the F here is going to be is just going to be this ratio that we spoke about. Okay. So now let's return to this example of 7 labs and 10 samples per lab. So here we have that I is equal to 7 and j is equal to 10. So therefore we have that I minus 1 is equal to 6. I times j minus 1 is going to be equal to 7 times 9, which is 63. And then ij minus 1 is equal to 69. So those degrees of freedom add up. So if we have our ANOVA table here, so this is going to be, so if we put degrees of freedom, SS, MS, and then our F. And then so this is going to be between, so this is between the 7 different labs. This is within the labs. And then this is the total kind of sum of squares of variability. The degrees of freedom we have here is 6, 63, and 69. Okay, and then if you calculate the sum of squares, I'll leave this for you as an exercise. So the only things you need to calculate here is to calculate SSB and SSW. SS total should hopefully be the same as that, but you can check that too. You should get these numbers, and 0.231 and 0.356. And then if you divide that by 6 and then by 63, you should get 0.021 and 0.0037. And if you do F, which is a ratio of these two numbers, so I'll put it down here explicitly, that should equal to 5.66. So your F statistic gives you a value of 5.66. And then under H naught, your F should have the distribution of F, and then the degrees of freedom should be 6 and 63. And you can kind of see that, if, for example, alpha equals to 0.01, if for example alpha is 0, then we'd reject H naught, looking at an F table. So you can look at an F table from the appendix or from from the web or anywhere else you can find an F table. And so therefore we conclude that the different labs have a significant effect. Because we can see that if we look at alpha equals 0.01, we'd reject H naught because like 5.66 is above the threshold that we're looking at. Okay, so just to kind of because this is a very important test, I just wanted to spend the last sort of 5 or 10 minutes just going over it. So general procedure for ANOVA F test, or I should say, this is one way. So for one way ANOVA F test, so we first want to find SSB and SSW, and you should check that should equal to the the sum of those should be SS total. And then we find MSB, which is SSB divided by I minus 1, and MSW, which equals to SSW divided by I times J minus 1. And then F is equal to MSB over MSW. And then check against an F table. And so it's usually helpful to explicitly write out the ANOVA table to keep track of degrees of freedom, SSB, SSW, etc. Okay, so that's kind of the general procedure for dealing with dealing with kind of one-way ANOVA. The last thing I just wanted to mention briefly is that if I is large, then H naught is like very, I guess we should say thin, because we require all groups to be the same, and so, for example, if you think about, like, for example, 52 states, so I equals 52. In that case, like, because all of the, you're saying that all of the groups have, or all of the states have exactly the same behavior, that's probably unlikely to be true. So, like, your, like, F-test will usually reject H naught. Reject H naught at any reasonable alpha level. And this is referred to as the problem of multiple comparisons. It's covered in 12.2.2. So in practice, we often want to correct for this. Want to correct, or rather than correct, because there's nothing like kind of incorrect about what's being done, but we want to correct or adjust for this. Because in some sense, like, rejecting H naught when I is large is, like, not in some sense super interesting, because it's kind of just telling you that there's a difference between these groups or labs, but it doesn't really tell you kind of where this difference arises. And so there are kind of ways to like do something a little bit more sophisticated than that. And to be clear, that's beyond the scope of this course. I just wanted to alert you to the fact that this is the case, because for most data sets that you apply this kind of ANOVA analysis to with an F statistic, you're probably going to reach the conclusion, unless you do something a little bit different, that you'll reject the null hypothesis. So I just kind of wanted to alert you to that fact. So that's it for one-way ANOVA. And in the next lecture, we're going to cover the more challenging case of where you start to have two-way ANOVA, where you essentially can have effects both of the individual and of the group. So yeah, that's it for today, and so we'll go into more details on this next lecture. Thanks very much.